Very often in mathematics, we are interested in ratios. Now, a ratio is simply a quotient of two quantities. And we can write it as a quotient, as in the form A over B. But in real life, you also sometimes see it written in the following way, as something like A colon B. And what this means is that for every A of the first kind of thing, we have B of the second. So, for instance, a recipe might call for the following. We might say, mix flour and water in a 2-to-1 mixture. This 2-to-1 right here is an example of a ratio. It's saying that for every 2 units of flour, we need 1 unit of water. Now, the point of a ratio like this is that we can give it without having to specify that whether we're talking about measuring things in terms of cups or liters or even grams or pounds. If we have a ratio of flour to water of 2-to-1, that means that we have twice as much flour as we have water. And so this kind of a ratio is one that we run into reasonably often. It tells us the relative quantities of the items that we're talking about without having to nail down what precise quantities they are. So for instance, a recipe might say something like this: mix flour and water in a 2-to-1 mixture, instead of saying something like mix 10 cups of flour with 5 cups of water. And by expressing the recipe as a ratio, it's more versatile. So you can scale it up or down easily depending on what you want to, how much you want to make. Now, what we usually do with ratios is we'll set them equal to one another. We'll want to know that one ratio is equal to another one. And there are lots of situations where this shows up. So let's look at a similar example. Let's say that a recipe calls for mixing flour and, let's say, salt now in a 200-to-3 ratio. So how much salt should we add if we are using 1,000 grams of flour? So this problem is giving us a ratio. It's giving us a particular relationship between flour and salt. We're trying to figure out situations involving figure out the amount of salt in another situation, but one that's going to use the same ratio of flour and salt. To solve a problem like this, we're going to use proportions. Now, proportions are an equality of ratios. It says that the ratio that we get on one side of the problem should be equal to the ratio that we get on the other side of the problem. So, for instance, in this problem, let's let x be the amount of salt we need to add to our 1,000 grams of flour. So what the recipe says is that we need to mix the flour and salt in a 200-to-3 ratio. So the way that we'll write that up in a way that's useful to us mathematically is to write that as a fraction. When actually going and doing computations, we'll always change all of our ratios into fractions. And it's often a good idea to keep track in the problem of what these quantities represent. This ratio, 200 over 3, corresponds specifically to 200 units of flour over 3 units of salt. And what we want to do is to say that fraction has to be the same as the fraction we get of flour to salt, the ratio of flour to salt, whenever we use this recipe, no matter how much flour we're using. So in this problem, we are using 1,000 grams of flour over X grams of salt. And this is an example of a proportion. It's an equality of two ratios. And so when you're told in a problem that two quantities have to be related in a certain ratio, that means that if you take their quotient, take their ratio, that has to be equal to whatever ratio you were given to begin with. So once we have this, we can solve for x fairly easily, and we'll use a technique that's often called cross multiplication, although I like to make things more explicit than just memorizing cross multiplication. So we're trying to solve the equation 200 over 3 equals 1,000 over x. Whenever we're dealing with a problem involving fractions, it's usually a good idea to multiply both sides of the equation by the least common denominator, or at least a common denominator. So in this case, I can multiply both sides by 3x, which is the common denominator of the two fractions on either side of this equation. When we do that, the 3's will cancel on the left, the x's will cancel on the right, and so we'll get 3, I'll actually write it as 200 times 3, times x rather, equals 3 times 1,000. And so notice what we've done. If we look at the transition from the original equation that we set up, 200 over 3 equals 1,000 over x, and that turned into 200 times x equals 3 times 1,000. One way of seeing what's happened is that we've taken each numerator and multiplied it by the opposite denominator. So 200 gets multiplied by x, 3 gets multiplied by 1,000. I do think it's important to keep in mind that this is just a shortcut for the process that we did above this line, where we're just multiplying both sides by both denominators. Of course, once we have this, then we are good to go, because now we get 200x is equal to 3,000, and we divide both sides by 200, so we get x equals 15. So that means that our answer is 15 grams of salt. Now, we can check our work. A lot of times when we're dealing with ratios, we can also approach the problem in other ways. Another way that we could have thought about this problem, and one that will be useful to us when we look at variation in a moment, is that the original information here, 200 to 3, says that 200 grams of flour corresponds to 3 grams of salt. And now, when we look at the question we're trying to answer, we've gone from 200 grams of flour to 1,000 grams of flour. And we want to say, well, how much have we increased that by? And we want to think of it in terms of how much have we multiplied it by. And we see that going from the 200 grams in the original problem to the 1,000 grams that we're interested in, we've multiplied by 5. And if we look at the amounts of salt that we have, we see that we went from 3 grams of salt to 15 grams of salt, which is also a product of 5. So what this shows is that when quantities lie in a given ratio, if you multiply one side of the equation by a number, or one side of the ratio by a number, you multiply the other side of the ratio by the same number. This is also related, everything is just other ways of talking about the same thing. This is also related to the fact that if I have a fraction and I multiply the same number on the top and bottom of the fraction, I don't actually change its value. So really all of these concepts, ratios and proportions, they are really all just following the same rules that we have for fractions. And so this is how we can use fractions and proportions in order to solve these kinds of problems involving ratios. So we can use the language of proportions to solve problems like this. We can also use the language of variation. And this language is a little bit more developed algebraically, mathematically, so we're going to be using a few more symbols on this one and defining a few more terms. So now let's talk about variation and proportionality. Let's let x and y be quantities. And we say that y varies directly with x, or an alternative way of saying this is that y is directly proportional to x if there exists a constant k such that y equals kx for all values of y and x. In this case, the constant k is called the constant of proportionality. So, to say that y is directly proportional to x means that y is some multiple of x. Notice that another way of writing this down would be to say that y over x is equal to k. for any x. And so in other words, the ratio of y to x is always the same. It's always the same number, k. Many things that we look at in science, in real life, can be described using proportions. So, for instance, we could say that the force required to stretch a spring is proportional directly proportional, I should say. When people use the phrase just is proportional to, they mean is directly proportional to. We'll see another version of proportion in a little bit, but directly proportional is the default. The force required to stretch a spring is directly proportional to the distance the spring is stretched. From rest. And there are a few things that we can ask based on this. A very common type of problem that you run into at this point would be the following. It takes 20 newtons of force to stretch the spring 0.1 meters. What is the constant of proportionality? So, for this type of problem, we need to do a couple of things. We need to introduce symbols to represent the various quantities that the problem tells us are proportional to one another. Then we need to set up the equation of direct proportion between them. And then we need to use data about a specific pair of quantities that go together in this problem in order to determine the constant of proportionality. So, for instance, we could do the following. We could let F, capital F, be the force required. We could let X be the distance the spring is stretched. And then the problem says that the force required to stretch the spring is directly proportional to the distance the spring is stretched from rest. Or in other words, F is equal to Kx for some constant K, which we're going to figure out. Now, we know from part one of the problem here that when the force is 20 newtons, X is 0.1 meters. So we can plug these numbers in. We could say 20 is equal to K times 0.1 and solve for K. So this is usually the first step in a problem involving direct proportions, is we want to know what the constant of proportionality is, because it's what determines the relationship between these two quantities. So if we divide both sides by 0.1, we get K is equal to, and this turns out to be 200. So that means that the constant of proportionality is 200 in this problem. And furthermore, this means that for any f and x, we have that f is equal to 200x. And so part 2 might build on this. Part 2 of the problem might say something like, how much force will it take to stretch the spring 0.25 meters. And in that case, now that we know that the constant of proportionality is 200, we can simply plug 0.25 into our equation, into the equation of proportionality there, in place of x. So we get F is equal to 200 times 0.25, which turns out to be 50. So our answer is that it will take 50 newtons of force in order to stretch the spring a quarter of a meter. And these are the standard types of problems that you can get with direct proportion. The other thing that we might do is it might not be the case that a quantity is directly proportional to just another quantity, but some algebraic expression involving that quantity. So we might have something like the following. The area of a circle is directly proportional to the square of its radius. So the way that we would write this is the following. If we let A be the area of the circle, and R is the radius of the circle, so now we'll say that the area of a circle, A, is directly proportional to, this whole expression is directly proportional to, turns into the equals K. Equals K times. So the area of the circle is directly proportional to, and then the last phrase, the square of its radius, will give us the expression R squared. So we have that the area of the circle is equal to some constant times R squared. Now, in fact, this is something we're familiar with, and we know that the constant of proportionality in this case is actually pi. We know that the area of a circle is equal to pi times R squared, and so that tells us that pi is actually the constant of proportionality in this expression, or in this equation. One thing that I want to note is that a direct proportion of the form y equals kx, which doesn't have this different algebraic expression here, always has a graph that has certain properties. That is a line. It always is a graph with a line with slope k and passing through the origin. So if we look at a graph here, or at a grid here, then the following lines could be lines that describe a direct proportion because they are equations of linear, or they are lines of linear equations whose y-intercept is at 0, 0. And the thing to note about these expressions here, like y equals mx, is that for any point on the graph, the y-coordinate is always a multiple of the x-coordinate. That's for any y equals mx plus b, where b is 0. The y-coordinate is always the same multiple of the x-coordinate, or in other words, the y-coordinate is proportional to the x-coordinate. Now notice that both of these qualities have to be true. We need to be looking at a graph that is a line and that passes through the origin. So for instance, this green line right here is not the graph of a direct proportion, proportionality. This is not the graph. This is not a graph where the y-coordinate is always some fixed multiple of the x-coordinate. So a direct proportion is one where if you increase one of the quantities, the other quantity will increase also, at least in absolute value. Things like with the radius and the area of a circle. If you increase the radius, the area of the circle is also going to increase. However, sometimes we have the opposite sort of arrangement, where if one quantity increases, the other one decreases. And so for that type of situation, we have what's called inverse proportion. So we say that y varies inversely as x, or y is inversely proportional to x if there is a constant k such that y equals not k times x, but k divided by x for all x and y. Again, k is called the constant of proportionality. So we have the same name for the constant of proportionality, and whether that k takes the role of multiplying by x or dividing by x depends on whether we have an inverse relationship from y to x or a direct relationship from y to x. So let's see an example. Let's take a slightly more abstract one now. We can say that y varies inversely as x. If y equals 7 when x equals 10, then what is y when x equals 4? So there are two steps to this problem that we can take. So first, y varies inversely as x. We want to translate that into the corresponding equation. That equation always means that y is equal to k over x. Now, in order to answer the final question, what is y when x equals 4, we need to know what the constant of proportionality is. When working with a problem involving proportions, either direct or inverse, we always need to be told some complete piece of data. We need to know everything that there is to know about at least one situation. So we need to have at least one part of the world where we know about all quantities involved. So we have that y equals 7 when x equals 10. And therefore, we can plug those into the equation in order to try to figure out k. So we have that y is 7 when x is 10, which means that 7 is equal to k over 10. Now, we can solve this for k easily. We multiply both sides by 10, and we get that k is equal to 70. So we found that the constant of proportionality for this problem is 70. So we have that our equation is that y is 70 over x. Now, notice that another way of writing this would be to multiply x on both sides and say that xy equals 70. In fact, This is always true for inverse proportions. If y is inversely proportional to x, that means that x times y is constant. X times y is always the same thing. Just like with direct proportion, if y is directly proportional to x, then y divided by x is always the same thing, is always a constant. With inverse proportion, y times x is always equal to the same thing. And so we can see from this type of equation that if x goes up, then y would have to go down in order to balance things out. Because if y goes up, but we need the product of x and y to still equal 70, then y is going to have to go down in order to accomplish that. And hence the inverse nature of the relationship between x and y. So now we can say, all right, well, what happens if x is 4? If x is 4, then y is equal to 70 divided by 4, which is 35 halves. So our answer to the question is that y would be 35 halves when x is 4. And that's it. Of course, we can plug this into a calculator also. If the problem wants you to approximate the answer, then you do that. You'll find that y is 17.5. So other than the different equation that you work with, y equals k over x, instead of y equals k times x, inverse proportions work basically the same as direct proportions. A quantity can be inversely proportional to not just x, but the square of x or the cube root of x, things like this. And those give rise to new equations. We can also have situations where a quantity depends on more than one other quantity. And this is the sort of thing that we call joint variation or combined variation. So we have joint and combined variation. So a quantity may be proportional or inversely proportional to several other quantities. So if y is directly proportional to, let's do x1, x2 up through xm, and inversely proportional to w1, w2 up through wn, then that means that y is equal to k times x1, x2 up through xm divided by w1, w2 up through wn for some k. So when you have a quantity that is proportional to several quantities, then all of the quantities that it is directly proportional to go in the numerator of this equation. All of the quantities it's inversely proportional to go in the denominator of the equation. So let's see an example of this. Let's say y varies directly as x and inversely as z squared. If y equals 40 when x is equal to 32 and z is equal to 4, what is the constant of proportionality? So here we want to start off by writing down the equation that's given to us here. Y varies directly as x and inversely as z squared. Don't forget to include the constant of proportionality. That won't be called out, but it's part of the statement involving the proportion is that we've got this constant k that sits here. So we have this equation, and we know everything about one particular point in possibility space. We know that if x is 32, z is 4, and z is 4, then y is going to have to be 40. So this means that 40 is equal to k times 32 over, now 4 squared is 16. If we simplify this down, 16 and 32 cancel to just give us 2. So we have that 40 is equal to k times 2, or in other words, k is equal to 20. So there's our answer for this problem. And so our equation for this problem, although it wasn't explicitly asked for us, is y equals 20x divided by z squared. And now that we have that, for any x and z we choose, we can figure out what y is. This type of problem actually shows up reasonably often in engineering and physics type problems. Let's see a couple of examples of that. The kinetic energy of an object is proportional to its mass and the square of its speed. The kinetic energy of a pardon me, the kinetic energy of a 6 kilogram object traveling at 1/2 meter per second is 3/4 joules. What is the kinetic energy of a 1,000 kilogram object moving at 12 meters per second? One of the interesting things about how these proportions work is that if you really do have two quantities that are proportional to one another, then you can take knowledge about what happens in a very small scenario and apply them to situations that on the face of it look very, very different. We're talking about a difference between a 6 kilogram object, which is about 13 pounds, traveling at 1/2 meter per second, which is actually pretty slow, much slower than most people will walk, or somewhat slower than most people will walk. And we're going up to a 1,000 kilogram object, the mass of a small car, traveling at 12 meters per second, which human runners would be challenged to meet. And yet, because it's the same physics applying in all those situations, the direct proportion applies the whole way, and so we can use this information. All right, let's go ahead and see how this goes. We have the kinetic energy of an object is proportional to its mass and the square of its speed. Let's give ourselves some symbols here. So let's let E be the kinetic energy. Often I would use K here, but we usually use K for our constant of proportionality, so I don't want to duplicate that. Although we can, of course, always use a different symbol for the constant of proportionality. So let's let E be the kinetic energy, let's let M be the mass, and let's let V be the speed. V for velocity, although I'm really here just using speed. So what the proportionality statement tells us is that the energy, the kinetic energy of the object, is equal to some constant times its mass and then the square of its speed. Notice I didn't say directly or inversely here, so I recall that the default is direct variation. So everything's being multiplied here. The kinetic energy is equal to some constant times the mass of the object and times the square of the velocity of the object. So now we plug in our known situation. So we know that E equals 3/4 when M equals 6 and V equals 1/2. So we have that 3/4 is equal to K times 6 times 1/2 squared. So we can simplify this down. We get 3/4 is equal to K times, now 1/2 squared is 1/4. So 6 times 1/4 is 3/2. Now to get K by itself, I'll multiply 2/3 on both sides. I'll multiply 2/3 because that's easier than dividing by 3/2 and it accomplishes the same thing. So then we can simplify over on the left and on the right, and we get that K is equal to 1/2. So there's our constant of proportionality. And by the way, these are all real numbers. So the constant of proportionality really is 1/2 here. And in fact, the energy of a moving object is 1/2 times the mass times the velocity squared. At least for objects moving at much, much less than the speed of light. Things get crazy when you start dealing with relativistic speeds. So there's our formula for the energy of a moving object, and now we can apply that to the problem that was asked us. What's the kinetic energy of a 1,000 kilogram object moving at 12 meters per second? So to answer that, we'll take 1/2 times 1,000 for the mass of the object times the speed of the object squared. So that's going to be 1/2 times 1,000 times 144. Now, to make this easy on myself, I'll say, okay, 1/2 times 144 is 72. 72 times 1,000 is 72,000. And therefore, our answer is that the kinetic energy of a 1,000 kilogram object moving at 12 meters per second is 72,000 joules. One thing you do have to be a little careful of when working with these proportions is, for real life problems, is that you do need to make sure that all of your units are correct. I'm working with joules, kilograms, meters per second here, and therefore I want to make sure that I'm using, I generally want to make sure I'm using similar or compatible units when I go to my question, or to answering my question. All right, so there's that example. Let's look at another one where things are a little bit different, where we aren't actually going to be given specific numbers. We're not actually going to work out the constant of proportionality, but we're still going to be able to answer a question about the situation involved. The gravitational force between two objects is directly proportional to their masses. So this is going to be treated separately. The mass of each object is going to be a separate factor in the equation. It's directly proportional to their masses and inversely proportional to the square of the distance between their centers. If two objects each double in mass but get 3 times further away from each other, how does the force between them change? Okay. So, that's a lot of information. Let's see how we can set this up. So first of all, let's get some variables. Let's let F be the force due to gravity. Let's let M1 be the mass of one object. M2, the mass of the other object. And then D, or actually, sorry, let's let R be the distance between them. So what our proportionality statement here tells us is the following. It tells us that the force between the two objects is proportional to, so there's going to be this constant out here, proportional to their masses. So that's going to be K times M1 times M2 divided by the square of the distance between their centers. So that's the equation relating the force of gravity to the masses of the objects and the distance between them. And this is, again, true. So now we want to know what happens if the two objects each double in mass but get 3 times further away from each other. We want to know what happens. So we basically want to know what happens to the force when we make certain changes to the quantities involved. So to do this, I like to set things up the following way. I like to call this the old force. That is the force originally before we've made our changes. And then let's write down what the new force is. The point is that we're going to use the same constant of proportionality. The same constant of proportionality will apply whether we're dealing with the original masses or the new masses. Now, the new force, after we make the changes, is going to be based on the following. So we're going to have K times the masses of the two objects, but now we've doubled the masses of each object. So instead of M1, we have 2 times M1. Instead of M2, we have 2 times M2. But the distance between them has tripled. They've gotten 3 times as far away from each other. And so the new distance is 3r. So our old mass was k times m1 times m2 over r squared. Our new mass is k times 2m1 times 2m2 over 3r squared. And we can rearrange this a little bit. Now on top we've got 2 and 2, which is 4. We can pull 4 out of the top, 2k m1 m2. And on the bottom we can distribute this squared through. So we get 9 times r squared. Now what you'll notice is that this whole expression right here is exactly what we started with to begin with. And this is what's always going to happen. If you change the quantities in a proportion by multiplying them by numbers, then when you replace all the quantities with their multiples, you'll be able to factor all those multiples out and get an expression that shows you what the quantity was beforehand. So we can write this as 4/9 times F old. So we get that the new force is 4/9 times the old force. So we see that in fact the force due to gravity after doubling the masses of each object but moving them to 3 times the distance from each other is actually less than half of the original. It's 4/9 of the original. So our answer could read something like that, as something like the force becomes 4/9 that of the original. That's the answer to how does the force between them change? It becomes smaller, and it becomes 4/9 of what it was before. And there are lots of patterns that you can start to look at. Many, many things in real life can be described using proportions, either direct or inverse. Direct proportions are slightly more commonly encountered, but the inverse proportions are very, very important, as in situations like this. It turns out that this inverse square relationship that we see here with a squared quantity on the bottom shows up not only when talking about gravity, the force of gravity between two objects, but also the electric force between two charged particles. It also applies to the amount of light that we receive from a light source, depending on the distance. The amount of light you receive is inversely proportional to the square of the distance. This inverse square relationship actually shows up all throughout physics and even mathematics. If you go on to calculus and even all the way to multivariable calculus, it turns out that there are very deep theoretical reasons for this. It's not just that the over r squared expression happens to show up a lot in real-world physics. It turns out that there's really important underlying theory there, and it really it sort of can't work in any other way and maintain the sorts of relationships and physics that we have. The r squared in the denominator, the squared quantity in the denominator, turns out to be very important to our real life and to the theory of what's going on in mathematics and physics.